Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest. Divide nodes into maximum number of groups. The problem is not that tedious, but it if you solve it via the first principles, as I always suggest, right? But looking at the solution, let me submit, like I just refreshed and I refreshed it again. So there are only 272 submissions as of me recording this video. So like a lot of people are not able to solve it, but we will look at how easy the solution is. Okay, and once you understand the solution, you will yourself appreciate that what like how easily you can solve this problem if you have started thinking from very basic. Okay, so with that, let's start. The problem is you are given a positive integer n, and you are given an undirected graph which have n nodes labeled from 1 to n. Okay, and as always, like there is a edges graph, edges array as well you will be given, which where ai comma bi represents that there is an undirected edge between ai and bi. Okay, you have to divide the nodes into m groups. Okay, and each group should belong, like each node in the graph should belong to exactly one group. Okay, and further, the constraint is, if a edge, or if two nodes ai and bi are connected with an edge, then they belong they should belong to adjacent group. So let's say ai belongs to group x, bi belongs to group y, then x minus y modulus should be 1. So they both should belong to adjacent group. Okay, so if these two conditions are satisfied, then you can say that okay, whatever you have divided, like you are dividing the graph, right? So whatever graph you have divided, whatever groups you have formed from the given graph is a valid division into m groups. Okay, now finally you need to return the maximum number of groups that you can form. So you have to find the maximum value of m, and if it is the case that there is no such m exist, you have to return -1. Okay, so that's the problem. Now you can see, uh, in this particular example, there are these many, like this is a graph, and one possible division into four groups is something like this. So you can see both these conditions are satisfied. The first condition, each node should belong to exactly one group. So you can see every node belongs to exactly one group, either 1 2 3 or 4. And each, like whatever pair, like whatever edges are there, let's say there are two nodes which are connected by an edge, they both belongs to adjacent group always. So you can see 2 and 6 connected by an edge, and 2 belongs to group 3, 6 belongs to group 4. Similarly, 1 and 4 is connected by an edge, 1 belong to group 2, 4 belong to group 3. And but if let's say there is an edge 1 to 3, if this edge was there, then it will not be a valid partition, because 1 belongs to group 2, 3 belongs to group 4, and the difference between them is 2. So they are not adjacent, right? So hope you understand what the problem is asking us to do. So you have to just determine what is the maximum value of m. Okay. Now, there are, as always, there are a lot of moving pieces in the problem. They have said that it is like graph may be disconnected. First of all, they have said the graph itself, like anything you are solving in graph might be tedious. You have to take care of various possible scenarios. So let's just simplify the problem, and let's say that instead of graph we are given a tree. Okay, that's the first thing we can simplify. Second, it is given that the graph is disconnected, but let's assume that the graph is always connected. So basically, we are given a tree of n nodes, and we have to solve the exact same problem. We have to divide it into m groups and find the maximum value of m that we can have. Okay, so hope the reduced problem statement is clear. So what is the reduced problem statement? Given a tree, everything is connected. Find me the maximum number of groups that I can divide it into. Okay, so tree would look something like this, right? A tree would look something like this. Now, in tree, because of the second condition, if you remember the second condition says that uh, every edge or every two nodes which are connected by an edge should belongs to adjacent group, right? So because this is an edge, right? Because of this edge, sorry, because of this edge, uh, 1 and 2 should belong to adjacent group, right? So if this is the case, like a simple strategy could be just give each one, just give level by level, right? Like just divide it into levels. So the first level you can just call it group 1, right? You can just call it sorry, so you can just call it group 1, call it group 2, 3 and 4. So there are four groups you have formed, and first group contain 1, second group contain 2, 3, 4, third 5, 6, 7, 8, 9, and fourth 10 and 11, right? This is a valid partition always, because first of all it is a tree, so there is no like there is no cycles or something like that, so you don't have to worry about it. Second, everything is connected, so every node is there in this uh, tree itself. So if you divide it just like that, you can say each, like this division is always good, right? Because every node is belongs to exactly one group. And second, every edge, like levels are found by edges, right? So you can see every, with every edge, the two nodes which are connecting those edges, which are connected with those edges, always belongs to adjacent group, right? So both the conditions satisfied, so this is a valid partition. Now this, like this is one of the partition, right? But we need to find out maximum value of m. So one possible value of m that we just found out was 4. Like we found out that m equals to 4 is possible, right? But we need to find out the maximum value of n, right? How to do that? So let's think about it. The given structure is a tree. We have already assumed that. Now what else you can do? Like first of all, if this is not the maximum value of n m, what else you can try? What is the best case? Let's talk about that. What is the best case? The best case would be a linked list. Let's say a tree was formed with three nodes, and it is something like this. The tree is something like this. Now if this is the case, you just form, this is group 1, this is group 2, and this is group 3, right? So basically this is a valid partition in case of linked list. But let's name it 1, 2, 3, right? Similarly, if you just root it at 2, like same tree rooted at 2 can give you something like this, right? And if this is the case, you will say that okay, first partition is this, second partition is this. So here m was 3, here m is 2. So notice how m is differing. M is differing based on what is the root, right? If root is different, we just saw that m can differ, right? So let's try that. Let's try the same thing in the current sample itself. So in this case, let's try to root the tree at 4. Okay, so this is the new root. Currently root is 1, so let's see what happens if we try to root the tree at 4. So if you try to root the tree at 4, like 4 will be at root, 7, 8, 9 would be the immediate children, 1 would be now a children, and for 1, 2 and 3 are already a children, and for 2, everything apart, like everything in the subtree of 2 would remain as is, right? So everything here is as is. So this is the new tree that we have now, which is rooted at 4. So now you can see, if you apply the same strategy, you will see, okay, I have 5 levels now. Previously we have 4 levels, right? But now I have 5 levels. So this strategy did works. Like basically, if we are changing the root, the value of m may change. Okay. Now what, like you have to find out the maximum value of m, right? So what you can do, simply just try out every possible route. Just try out every possible route, build the tree, find the value of m, find the depth, and that's the value of m, right? So hope this point makes sense. So basically, we just saw that okay, uh, given structure is a tree, and because it is a tree, the first condition, like because it is a tree and we can just lay it down in a top down manner. We can always found out a valid partition. There will be always one root, that is sure, because this is a tree, right? There is no cycle, so there is only one root. Because of that, you can actually divide it into groups level by level, and each of these level would be a valid tree. Sorry, would be a valid partition. Now we started the levels by one, and that found like that leaves us with the valid partition. Similarly, we saw that if we change the root, the number of levels are changing. So what we are saying now is, if we try every possible level, every possible value of m, we will get all the possible value of, sorry, if we try every possible value of root, we will get all the possible value of m, and we will just take the maximum. That is our answer. So hope the solution in case of a tree is clear. In case of a tree and it is connected, both the conditions we have assumed, and because these two conditions are true, this solution does make sense, right? Now, uh, because this, like we have just solved this for a tree, right? Now, let's just like first of all, I'm not showing the pseudocode for this, because this is this is very simple. You just need to find out the depth of the tree given a particular root. So I'm assuming that you all know this. Now we need to solve the second. Like, let's make the problem a little bit more difficult by saying that we previously we assumed that like our structure is tree as well as the tree is connected, right? Let's just keep the second constraint as is. That is, tree is still connected. Like, we are still ignoring the case that the graph may be disconnected. But now let's assume that the given structure is not a tree, it is a graph. So what could happen in a graph? You can still lay down in the same fashion, that is fine. But what could happen in a graph is, you would have other edges like, sorry, you would have other edges like this, right? Or maybe this, right? Now, because of other kind of edges, the structure would not be a tree. There will be cycles and other things. But we are assuming that the entire structure is still connected. We are not ignoring that fact. Okay. So now we have to just solve what is the maximum value of m in this particular structure. Okay. We can try the same strategy, exact same strategy. Just try out every possible route. You will get a value of m, and that would be your. Just take the maximum, and that would be your answer. Okay. Now, finding uh, whether a particular m is correct or not was easier before, because there was no cycles, right? And so because there was no cycle, there is only one such possible combination or one such possible structure with a given root. But now there are cycles, right? So let's just simplify this a bit. Let's say there is only one, no, one edge, 11 to 6 is there. So you can see there is now a cycle which includes these all nodes, right? Now, because there is a cycle, the given structure can change. How it can change? You can see 5 goes to 11 and 11 goes to 6, right? So what, like one of the possible structure could be this. The given structure is one of the possible structure, but other possible structure could be that 6 is not there, 6 is here, right? So 6 is here, and because 11 to 6 was a root, like was a node, so this edge is there. And if you remember that 2 to 6 was also connected, so this is another possible structure, right? Because there are various possible structure, like this is another possible structure, there can be other structures as well given the different edges. Because there can be different possible structure, you can't deterministically say what is the value of m, or basically every possible structure would not be valid. Like for example, if you just partition it in the previous way. Let's say you do DFS and you get this. So you partition it in just like the previous way, assign every level to a single group. And now if you see, this is not a valid partition. Why? Because 2 to 6 is an edge and 2 belongs to group 2, right? 2 belongs to group 2 and 6 belongs to group 5. As the difference is not 1, so this is not a valid partition. So basically what I'm trying to make here is, if there are edges or which makes the tree non-tree, where basically there are cycles, then we can't deterministically say what is the value of m for a given root, right? We can still the same strategy still makes sense. For a given root, find me m, and I will do that for every root and take the maximum. That is my answer. That still makes sense. But for a single root itself, there are various possible combinations. We just saw one possible combination where the tree, like the given partition set, is not valid. And similarly, if we just ignore this entire thing and just go by the previous state, like this is the state previously, right? Just go by this, and now if you divide it again, this is indeed a valid partition, right? So for the same structure, we are getting two different partitions, and one of them is valid, one of them is not valid, right? So what you need to do is you need to find out a valid partition for a given root m, sorry, for a given root r. So how can you do that, right? So think about it. Why previous one was not valid? Previous partition, or let's just go to that state again. uh, we are talking about this case, sorry. So let's just remove this and this. So we are talking about this particular case where this, sorry, this is an edge and this is an edge, right? So this was not valid because there was 2 belongs to level 2, group 2, and 6 belongs to group 5, right? And why it was not valid? Because there was an edge, right, which actually got discovered after some time. If this edge was discovered as soon as we were traversing the child of 2, if this edge was discovered at that time, we would have got a valid partition. So basically, if we currently, we can get this structure if we do DFS. Like we go here, then we go first here. We'll explore all the child of here, and while exploring all the child of here, we will go there, then here, and then we will come to 6, right? And finally we will get this structure. Like after this we will then try, like the parent of 6 is now 11, and now we will, like after exploring everything here, we will go back to 5. 5 has everything explored, we will go back to 2, right? And now 2, we will now discover that okay, 2 has also a edge which goes to 6, because we discovered it late, right? That's the point. We were missing the condition. The condition was every group, or like every edge should connect two nodes which belongs to adjacent groups, right? And because this edge was discovered late in the process, we kind of get this particular structure instead of the previous structure, right? So what is the solution? The solution is simple. Because you want every edge of the parent to be visible just now, you will do BFS instead of DFS. That's the crux. Like notice that why this entire thing was an issue. This entire thing was an issue because 6 was discovered after 11, but 6 is also a children of 2. And because this is the case, there, like with 2, like 2 belongs to some group which is up, higher up in the ladder, and 6 belongs to some group which is lower, right? But if we would have done BFS, then we would have uh, started with visit all the children first, visit all the children of one first, and because we have visited every children of one first, we are sure that the next group would be, or the next set of nodes which belongs to that group is a valid, is valid because every children of one was visited, right? Similarly, if you make sure that before visiting 5 you visit every children of 2, 3 and 4, then you will not have these cases. Basically you will ignore this case, and 6 would be visited just after this, right? And because 6 is visited just after this, you will form a valid group, valid next group. And the next thing is, while traversing the next group, there can be cases where you are going upwards, right? There can be this kind of cases. And if this kind of cases exist, you will say that any possible solution or any possible uh, arrangement of these nodes will not form a valid partition, right? So 11 to 3, if you will not, you will never get something like 11 to 3 and 3 is not visited because you are doing BFS, so 3 would be already visited, right? And because 3 is already visited, it means that there was an edge with its parent which led the discovery of 3. So 3 belongs to an upper group, right? Now, if there is a back edge, like let's say you are visiting the children's, and now you see that okay, from 11 there is a back edge to 3, and if there is such an edge, you will see what is the level of that node. The current level is 2, right? And what is the level of the parent node which is leading to the current node? It is 4, right? And you will just find out the difference. If the difference is more than 1, it means that this edge or this node was discovered by someone which was upper in the process, and because this that node has this children, so this discovery was essential. Otherwise you would end up having the same issue that we just discussed, right? So to avoid that, you just visited that node first. So this edge is necessary, this is very important, because otherwise this edge might get discovered late and you will end up in the same issue. Because of this edge is important. This edge is now fixed, and you have a back edge from 11 to 3, right? And this back edge is 2 up, or like this back edge lead is connecting a group 4 node to a group 2 node. And because this is the case, you will straightforward return -1. This is like any possible uh, arrangement having root node as 1 is not possible. I will repeat, any possible arrangement having root node as 1 is not possible, because it leads to discovery of some node which is getting discovered by lower nodes as well. And because we can't remove this at all, because we want to satisfy that every node or every edge connects to node which are belonging to adjacent group, this edge we can't remove. Like this, we can't change the position of 3. So because we can't change the position of 3 and 11 is also fixed, and this are connecting two nodes which are not adjacent group, we will just return -1. Okay, so if you think about it again, in the previous case, if we follow the same strategy, 11 will be connecting to 6, right? And if 11 connects to 6, that is fine, because you will see okay, 6 was discovered by 2, right? And 11 connects to 6, so 11 is indeed connecting to someone which is just above it. So this arrangement is valid, right? So hope you get the intuition. So what we are doing is, we are still finding out this, we are still following the same strategy. I will route every, I will try every possible route, find a valid structure, and like find a valid structure, and from that structure we will get some value of m, right, for this particular root, and we will try out for every possible root. This, let's say we got m1 with 1 as root, m2 with 2 as root, and so on and so forth, and just take the maximum of all of this. This will be your answer, right? Now the only difference here was there can be multiple possible configuration for a single graph, and because of that there can be two configuration, one of which is valid, one of which is not valid. So we need to find a valid configuration. For that, what we said that instead of doing DFS, we will now do BFS, because we want every edge which is connecting two nodes to belong to exactly adjacent groups, right? And because we want every edge to be in adjacent groups, whatever group was there before, the next node should belongs to the very next group. Because of this, we will do BFS. So because DFS, doing DFS will not like will may lead to an inconsistent state, right? So we will do BFS, and because we are doing BFS, adjacent criteria will always be satisfied, right? Now there can be cases where the below nodes also discovers something above, right? And if that's the case, what you will say, okay, uh, I this node, like this node was necessary because of this edge. So this node value, this node position is fixed. This will belong to group 2. Now, if this edge is requiring that any node in group 4 should connect to any node in group 2, this is not a valid edge at all. And because of this, there is no possible valid configurations that you can make which have root node as 1. And you will just return -1 for root node 1. You will still try other possible roots and you might get valid configurations. But for root node 1, that is not a valid configuration. Okay. So hope this makes sense. Let's look at the pseudocode for this. Again, currently we haven't explored, or we haven't relaxed the constraint that the graph is disconnected, but it is very simple. We'll look at it, but for now let's look at the pseudocode where we have a graph, or we have a connected graph, and we need to find the maximum value of m. So what we are doing is we are trying out every possible route, right? And now we are doing BFS. So this is standard BFS code. What we are doing, we are maintaining the levels as well, because we just saw that we need to uh, take care of levels, right? So we are maintaining levels as well. Initially we put root in our queue, right? Now this is standard DFS. While queue is not empty, we pop out the current top from the queue, and now for each child of the current, right, for each child of the current, we will uh, what we will do, we will just see whether the level child is -1. Level child is -1. If this is the case, this means this node is not visited at all. Like initially we are initializing everything is -1. So if this is the case, the current node or current children is not visited at all. So this is fine, you can visit it. But if current children is visited, right? If current children is visited, so this is just a implementation. You can just put queue as well if you are thinking why this is next level queue. But this is just an implementation detail. So if current child is not, if current child is already visited, like if level is not -1, it means current child was already visited somewhere, right? And if it is already visited somewhere, that somewhere should better be current level or current level -1. Now, why these two cases? Let's look at it. So let's say you are at this level, like you are visiting 2 currently, right? You are at this level. So this is your current node. Now, when you are visiting the children of 2, you will get 1, right? You will get 1, and because you will get 1, you will not say that this is not a valid configuration. You are visiting children of 2 and you get 1. You will not say this is a valid configuration. This is not a valid configuration because 1 was already there in the group above, and because of 1 only 2 was discovered, right? So if the node is the parent, if the node is the parent, you will say I am okay, uh, like this edge is still okay. Now if let's say there is an edge like uh, 2 to 5, right? And level of 5 is uh, or let's say like you are okay. Let's change the example first. Okay, so let's say you are visiting this level. You are currently at this level, right? Now if you are currently at this level, and let's say you are visiting the node uh, 1, right? And there is a edge like this as well. Like there's an edge from 2 to 7 as well. Let's just put it this. So there is an edge from 2 to 7 as well. Now you are traversing all the children of 1, right? uh, so if you are traversing all the children of 1, this 2 might have been like this. First of all, children of 1 is 4 as well, right? Because this is bidirectional edge, right? So if children of 1 is 4, you will say that okay, this is fine. uh, I like this parent. If I am pointing to some my parent, that is fine. I will skip this case, right? Otherwise, if I am pointing to someone like which is already which already has parent, let's say I am pointing to 2, right? And 2 already has a parent, right? Or let's say let's say there is an edge. How could I explain? Let's say there is a node X, and there is a edge like this, right? So now one was discovered because of force, that is fine. But if this is the case as well, like one has a edge with X as well, then this is also okay, right? Because this is just the above layer. So anything just above me should be fine. And that's what we are checking with this condition, right? So first thing is current level. We are checking current level because uh, the children will be at next level. So if the node is at current level, that is fine, right? Similarly, we are checking current level -1 because of parent. Like you can just remove this condition if you are maintaining parent as well. Like if we keep maintaining parent as well, we can just place. If it is parent, just continue. So the condition was placed because of parent, and the test case I think was weak because of this. It passed, but you can just put parent condition here. So hope this entire thing makes sense. What we are doing, the exact same thing, trying out every possible route and doing BFS. Only condition we want to check here is if there is a child which points to somewhere above 2 levels, right? Then we will just return -1. That's the only condition we will check. Otherwise there is normal BFS, and finally we get the number of levels in the tree. Okay. uh, so this entire thing is for the case where the tree or the graph is completely connected. But in the question it was given that the graph can be disconnected as well. So let's say this is the graph. There are 11 nodes, and these are the configurations of these 11 nodes. Now if this is the case, what you can do, you can solve each of them independently. You will solve this independently, you will solve this graph independently, and you will solve this graph independently, right? Now let's say from this you get 3, that the number of level possible is 3. Like value of m is 3. You get 4, you get 2 from here. Like the value of m is 2. Like there can be more, but for now assume that it is 2, right? And let's say after solving this you get -1, that there is no possible valid configuration. So what you can do, you can just if any of them is -1, then your entire answer is -1. You can't do anything. But let's say if this was not -1, and instead this is, let's say, some 1, or so, what you can do, you can just sum them all up. Why sum? Because what you can actually do, you can put this graph like this. So everything sorry so everything let's just put it here. So what you can do, you can just imagine this graph as this. So you will just found out the levels here. Again, this might not be a valid configuration, like this is not a valid configuration at all, but this is just for example. You can just think of the levels like this, and both of the conditions will be satisfied. Every node is belonging to exactly one level, and every edge is connecting to adjacent level, right? So basically whatever the value was there for the first graph, x1, right? Whatever the value, sorry, whatever the value was there for the first graph, x1, x2 for the second graph, x3 for the third graph, you will just sum them all up, and that will be your final answer. But if, as mentioned, if any one of them is -1, you will return -1. Okay. So hope this entire solution makes sense, right? Uh, just to reiterate, what we have done, we have started with a very simple problem where the given configuration is a tree and it may not be connected. Then we have divided the problem by saying that, okay, the configuration can be cannot be a tree, like there can be edges which form cycles, but it is still connected. So for both of them, we tried the same approach. We tried every possible route, and we find out what is the value of m that can be there. For tree, it was simple because each, like, there are no cycles. But for graph, it was a bit different because there are cycles. There can be two possible configurations, one of which is valid, one of which is not valid. So what we have seen that, okay, if like I need to place two nodes which are connected by an edge in two adjacent groups, right? Because of this, we tried BFS, because if you do BFS, every edge that we get, we are sure that we are getting all the edges of the parent first instead of doing DFS, where we visit all the children's first, right? Because of this BFS strategy, we now found out valid layers. Now, if there is a back edge from some node to upper nodes, then this back edge will either better be just above this layer, and if it is just not above this layer, it is the back edge between two levels which are greater than 2 of distance apart. We will just say that this configuration is not possible because the previous node was the position of previous node was fixed because of some other node in the hierarchy, and we can't remove that position because otherwise the entire structure would be different. So because of that, we figured out that, okay, that the position of whatever node this is pointing to is fixed. So if the node is pointing to someone which is at distance more than distance 1 apart, I will not get a valid configuration at all with this particular route. Okay. So after this, we relaxed the constraint of disconnected graphs as well, but we said that uh, we can solve for each of the graph independently and just sum their answers up. And one case that we discussed was, if any one of them is not possible, the entire structure would not be possible, right? So let's look at the code. The code is exactly what we just discussed. So there are okay, so I have refreshed this, so this expanded everything. Okay, so what we have done is we have just built our graph first, right? As this is very simple. Then what we have done, we have found out the components. We have found out the connected components. So basically, we have different graphs which may not be connected. So we found out how many different graphs are there. So we found out these graphs with independent components. We look at what connected components are. Once we get that, we are finding the answer for each of these components independently. Now remember that now this component is a valid connected graph, and we know how to solve that, right? So we just solve that independently, and finally we store the result of every such component in results array, and we see if any of them is -1, we return -1. Otherwise, we will just sum everything up and return the answer. Okay. So now let's look at the connected components code first. So this, what is the motive? Motive is to find out how many different graphs are there or how many different components are there which are connected. So what we have done, like if you try to find, this is very standard problem, you can just search it and you will get it. But the crux is you will, okay, let's clear this up. That will make things clear. So what you will do, you will start DFS from any node, DFS or BFS, your choice, and you will visit everything that you can visit. That's it. Let's say I started from this node, I visit this node, this is not visited, I visit this node, and now I can see I can't visit anything else. So whatever nodes I can visit from a particular node which is not yet visited, that belongs to one component. So that's what we have done. We have just maintained a visited array which everything is false, and now uh, we just started DFS if the current node is not visited. If J is not visited, I'm just starting DFS from J, and I am all like in the DFS itself, I am pushing which nodes I visited currently in a vector, and finally I push that vector to my components. Okay, so now this inside the DFS, what we are doing exactly this standard DFS. We check whether the node is visited. If it is not, if it is, this is done. If not, we will visit it. We will push that node to our array and then visit all its children. That's it, right? So this will give us the candidate components. Now, if you remember, we have to solve the problem for each of the component independently. So this is what the code is. So what we are doing, the same thing, we'll try every possible route. So we try out every possible route. We found out the value for a single route, right? And just return the result. So let's look at what is the value for a single route. This is exactly BFS that we just discussed. So we initialize the levels, we initialize our queues, and then we just do BFS. And inside BFS, like this queue equals to next level is something that I usually prefer while implementing BFS, but this is completely optional. You can implement BFS using your own strategy. Uh, Now, the major thing here is this case where we are saying that, okay, if child is not visited at all, that is fine, just push it. If child is visited, just check whether what is the level of the child. Level of child is current level or it is current level minus one. If any of them is not true, it means I am the child is pointing to someone which is much higher than me. So this entire condition is not possible. The entire configuration is not possible. So I will return minus one. Okay. So hope this entire solution makes sense. If you have any doubts in this problem, please post them in the comment section below. I know it might sound a bit tedious, but I think you really appreciate if we how we started the problem. We started with a simple tree, and then we started with how I actually like we started with simple tree, and then we found out that okay, I can solve for tree independently. Now let me introduce a graph constraint here, and then let me introduce the undated component here. So if you like, I exactly followed the same strategy. My thought process was exactly similar in the live context as well. So hope you get to learn something new. If you like the video, give it a thumbs up and do subscribe to the channel if you haven't already. And I will see you in the next one. Thank you.